Welcome back, everybody, for the second and already last session of today, which is also Karen's second session.
Okay, so back to our principles, holography, and infinity. And today I'm going to be talking about the role of singularities in the search for quantum gravity. So the principle of singularity resolution. And it's going to be based on a recent paper that I wrote with Sebastian D. Harrow called 4 Attitudes Towards Singularities in the Search for Quantum Gravity. So a bit of a revision here again. We have several different approaches towards quantum gravity, taking these different motivations, different understandings, what the theory is supposed to achieve. And we're relying on various different means of non-empirical theory assessment. Each approach is kind of using different principles in motivating and constraining and as means of confirmation. So I've suggested that we might understand the problem of quantum gravity as finding the set of principles that we take as constraints, the way of defining the theory. What is it that we're expecting the theory to do? Why are we looking for it? And then to try and get a better philosophical handle on this, some clarity. So singularities in GR and in QFT, they're often taken to motivate quantum gravity, so being used as a guiding principle. But also it's often used as a constraint or a means of confirmation. Particular singularities are being resolved in the approaches. This is taken as indication that they're on the right track, or indeed we might expect that it's necessary. We need a theory of quantum gravity to resolve some of these singularities. So then we can ask, well, do the singularities actually represent an incompleteness of our theories? And of course this depends on the particular types of singularity. So yeah, you've seen lots of these sorts of quotes, particularly for GR, that singularity theorems imply that GR contains the seeds of its own destruction. Something like this, a computing machine calculating a step ahead of dynamical evolution of geometry. We come to a point where it can't go on, smoke begins to pour out of the computer, theory is just totally broken down. Things like this. So probably I don't need to go over them. You've seen these sorts of quotes that, you know, it seems like the singularities are the doom for GR and really strongly motivating the need for a new theory. But on the other hand, we have some philosophers and some other physicists who don't take them as necessarily problematic. Maybe we can be comfortable with the singularities. So here's Ehrman saying that the existence of space-time singularities need not mean that GR contains the seeds of its own destruction, and that this kind of generalized horror of singularities is not justified. So, do they represent an incompleteness of our theories? Well, it seems like physicists tend to say yes, philosophers, a bit more cautious, tend to say no. So, in the paper, we have a look and kind of ask, well, in what sense does GR break down? And we also present these 4 different attitudes we can take towards singularities in regards to the search for quantum gravity. So, yep, I'll start by talking about singularities in GR, then look at singularities in quantum field theory, and then present kind of the 4 attitudes towards singularities that we could have in quantum gravity. And emphasizing that of the 4 attitudes, you can take different attitudes towards different types of singularities. It's not like every singularity you have to have the one attitude towards. Okay. So, singularities in GR, some pathologies of the space-time, they can be of various types. There's difficulties in defining exactly what they are. We have this large family of conceptually distinct but interrelated pathologies. And of course, the Penrose-Hawkins singularity theorems show that singularities are unavoidable in GR under some very reasonable conditions, notably our black hole singularities and Big Bang singularity. So we have two main classes, being the geodesic incompleteness and the curvature singularities. So starting with the geodesic incompleteness, the idea is that a space-time is singular if and only if it contains an incomplete, inexpandable time-like geodesic. This is kind of the official definition. And it corresponds to this intuition that kind of have missing points of space-time, just points where the metric tensor is not well defined or that has been cut out, if you can make sense of this. So does this represent a breakdown of GR? Does it represent an incompleteness? Of course, Curiel, Ehrman, and following Meissner as well, it's not exactly clear in what sense this could represent a breakdown. Because we're thinking, of course, about the space-time, there's no actual missing points there. So there's just no singular points of space-time where the laws of GR fail to apply. So Ehrman suggests that we should take singularities here as kind of a prediction of GR. Again, following Meissner, saying that there's kind of no reasonable point to try and anticipate failure of the theory here. They're just not there. But there's still a physical worry here, in that there's this possibility that you could have a freely moving observer, particles, who just kind of pop out of existence. So this seems troubling. So the worry here is that the geodesic incompleteness leads to a lack of predictability or conflicts with determinism. If you think of GR as otherwise deterministic theory, and then it's these points where things can pop in and out of existence is breaking that determinism. So it could indicate the theory is incomplete. In particular, Ehrman emphasizes that if this breakdown of determinism were visible to external observers, then we are, being sprayed by these unpredictable influences. And yeah, if we're thinking of GR as a deterministic theory, and then it's coming up with these things, even though we've set it up as a deterministic theory, we've got this nasty form of inconsistency here. He says the laws would perversely undermine themselves. So, does this inconsistency motivate the need for a new theory? And yeah, if you've read Ehrman, you'll get the jokes here. So, maybe not. You might think, well, GR is not necessarily deterministic anyway, so having this extra inconsistency isn't so much of a problem. You might just think it's okay to have an indeterministic fundamental theory or not be bothered. And also, maybe we have a strong form of cosmic censorship where this indeterminacy is just not visible to anyone anywhere. And so you'd avoid that charge of contradiction between a deterministic theory and its indeterminism. So just a little bit on cosmic censorship. We have,
But the question is, in what sense do you say that GR is not deterministic anyway?
Yeah, I would ask Chris about this because he's more expert on it. Different forms of determinism, yeah. So we have various proposals attempting to save us from whatever these harmful naked singularities are. A very weak form, weak cosmic censorship just hides them behind the event horizon. So if you're external, you'll never see any of these horrible things popping in and out of the singularity. But this kind of cosmic censorship is not going to save you from the charge of incompleteness of GR. Because if space-time still exists beyond that horizon, and GR is not determining what goes on there, then you could make the claim still that the theory is incomplete, even if you don't see it as an outside observer. So there's a stronger form of cosmic censorship, holding that the breakdown of determinism occurs beyond the Cauchy horizon. So this is inside the event horizon. And beyond this surface, the Einstein equation no longer gives the unique solution. So I've just borrowed some diagrams here. I don't have the pointy thing, but the idea here is that in this space-time, you've got the point P1, and from the initial data on this surface, you can determine what goes on at P1. But over here, you've got point P2, which is kind of beyond the Cauchy horizon, and you can see that its initial data, it's intersecting with the singularity here, and so you're not going to be able to get any knowledge of what's going on here. It's not being uniquely determined anymore because part of the past light current is in the singularity. So that's going to be for any point beyond the Cauchy horizon. So the strong cosmic censorship hypothesis just wants to kind of get rid of these Cauchy horizons. If they're not there, then we're not going to have this indeterminism. So Penrose proposed that the appearance of this Cauchy horizon is non-generic, and that it's just not going to form, is some way unstable. So instead of space-time continuing after that horizon, it just ends at a space-like singularity across which the metric is inextendable. So if this holds, then we would ensure that there's no violations of predictability anywhere, even by local observers. The idea is that you're falling along, you don't see any problems until you just disappear. And of course, you're not going to notice the problem when you disappear either. So the singularities are harmless there. But it would seem then that whether or not geodesic incompleteness is problematic for determinism will rest on the fate of this strong cosmic censorship. It's still open here. Hawking really wanted it to be true, so he made a bet, which I think is still open against Prescott thought. I found kind of an interesting recent paper that's looking at curved spacetimes, so dynamical rotating black holes without symmetry, and that paper argues that the strong cosmic censorship conjecture is violated for those spacetimes. They argue that the spacetime doesn't terminate at that space-like singularity that Penrose envisaged. And so spacetime does extend beyond the Cauchy horizon, but the spacetime there is pretty messed up. It's not sufficiently smooth for GR to hold anyway. So there's no indeterminism introduced into GR, even though spacetime does extend beyond the Cauchy horizon, because GR itself doesn't apply here. So I guess it saves GR from the indeterminism, but for our purposes, I think this is still problematic because we've still got an incompleteness of the theory. We have space-time beyond this horizon, but GR is not telling us what happens there. So it's motivating the need for some new theory. Okay. So, yeah, this is open, I think, whether or not the geodesic incompleteness is motivating new theory or not. And it does seem to rest, I think, on this strong cosmic censorship. So coming next to the curvature singularities here, the idea is that some quantity blows up. So this one, it seems to be discussed a bit less, but we do physicists do tend to think of this as problematic, and we've seen some people already mention this throughout the conference. We think this one's kind of more of a stronger reason for thinking that GR breaks down because of an effective field theory argument that I'll present. But another reason why this one is perhaps more interesting is because it can apply, for instance, to strings that might otherwise be able to avoid the geodesic incompleteness. This one would still hold. The basic argument is that you're treating or thinking of GR in framework of effective low energy quantum gravity. So just including these higher order corrections, higher curvature corrections to the Einstein-Hilbert action here. And these are just general curvature corrections. The idea is that these aren't forbidden even in the classical theory. So even though we don't ever need to use them, they could be there. Right. So we can take into account the possibility that such terms exist. And then the idea is that if you have a model of GR with the curvature singularity and then compare it with a model of GR with these curvature corrections, they will correspond for most situations. But the idea is that when we have this curvature singularity, the higher curvature terms will start to dominate over the Einstein tensor. So here you can see that GR is no longer giving us the right predictions in this regime. So this is, I think, the strongest sense in which the curvature singularity signal that GR breaks down. Okay, so that's the singularities in GR. Now look at the singularities in QFT. So we have a lot of divergences in quantum field theory, IR divergences, which I won't discuss, UV divergences, we also have Landau poles, and the perturbative non-renormalizability of GR. So I'll go through those last three. Okay, so of course the UV divergences, they occur in what's known as conventional QFT, or Lagrangian QFT, or QFT with cutoffs. Of course, these terms come from David. So the framework within which the standard model of particle physics is formulated. And famously, calculations were historically plagued by infinities, mainly due to the reliance upon perturbation theory, because this involves summing over all possible intermediate states. There are infinitely many at all orders of perturbation theory, so we get these divergent integrals. And this is really coming from the heart of the formalism, the way you've set it up. Because you're integrating over all the momentum energy states and the local nature of the dynamics, point-like interactions, kind of leads to this situation. So, of course, to deal with this, historically, for instance, in particular theories like QED, you would introduce your finite value cutoff, renormalize, and you get a theory that gives you finite answers, and really good answers. It works really, really well. And yet, historically, there was this suspicion that a bit uncomfortable with this. What's going on? We've just kind of swept the infinities under the carpet. So this perturbative approach to QFT seemed to be intrinsically approximate, conceptually problematic. So one response to this kind of suspicious state of affairs, of course, was the attempt to develop a new formulation of QFT, just laying out different axioms, very mathematically rigorous, and just ensuring that we don't get those divergences in the first place. So lay out these mathematically rigorous axioms and then construct models of these axioms. So we have axiomatic QFT and then constructive QFT. And then an approach known as algebraic QFT is the most promising proposal for the axiom. So this approach towards dealing with the singularities in QFT, it's not an attempt at getting quantum gravity. In fact, it's like explicitly ignoring. It's just working kind of at the level of QFT, being a combination of special relativity and quantum mechanics. So it's not aspiring at anything deeper, and yet it's expecting to have a nice theory kind of at this level already. Okay. But meanwhile, back in the mainstream high energy particle physics, there was the development of the renormalization group. So this led to a non-perturbative framework and the discovery of the standard model. And the idea is that just evaluate the theory to some finite cutoff, and then the effects of all these high momenta degrees of freedom at lower energies get encoded in the dynamics of the low energy effective theory. And kind of the magic of the renormalization group analysis is this demonstration that the low energy effective theory is insensitive to the means by which the cutoff is introduced. So the only effects that are significant at the low energy where you're using the theory changes in the coefficient of finite magnitudes. So this is great, but it's giving us very little indication of what lies beyond. So as David says, renormalization theory itself tells us only that if there is some short distance cutoff, the large scale phenomenology will give us almost no information about its nature. So we don't know what's going on beyond this. But nevertheless, in the case of these UV divergences, the suspicion is that they're not reflecting anything physical. It's just due to the limitation of these theories. So treating the framework itself as inherently approximate, and the models, theories we're constructing using it, are understood as effective theories, meaning that they're just not valid to arbitrary high energies. So yet, whatever this unknown physics beyond is, which could be many different things, the success of our current theories are explained already thanks to the renormalization group. Okay, so this is important because the need to employ a short distance cutoff here is not taken to indicate anything about the physics beyond, and it's in contrast to the case in condensed matter physics, of course, where we also use renormalization group techniques and get divergences at high energies. But here we have external means. We can look at the system and we know that this continuum approximation doesn't hold high energies anyway, because once you get to the atomic scale, you have this kind of cutoff. So we have evidence for a real physical cutoff in the case of condensed matter physics, but it doesn't apply in the case of quantum field theory. So it's not giving us evidence that we have an analogous discrete structure of space-time, for instance. Because it's very possible that these UV divergences simply reflect limitations of the theory rather than any new physics. Okay, so those are the UV divergences. Now look at the Landau poles. These ones are kind of thought to be more concerning because they're not thought to be due merely to the limits of perturbative analysis, and yet, the little asterisk there is that the way they're calculated, it is through loop first order and second order loop calculation. So it is still kind of using that framework anyway. It's not completely shown that this is true, but the feeling is that it is. But what the problem is that we can have renormalizable theories such as QED, which we'd expect to be able to use then But what you find is that coupling actually grows, and it's expected to become infinite at a finite energy scale. And this is an unimaginably high, though finite energy scale here. You can compare exactly how much bigger it is than the Planck length. So you can see then that we would normally just kind of ignore that. But one way to avoid the appearance of the Landau pole is by kind of setting that renormalized charge to 0. So the idea that it goes to 0 as the cutoff goes to infinity. Physical interpretation of this is that it's being completely screened by quantum fluctuation. So this would be a case of quantum triviality. So it kind of means that the theory has no interactions, and that's the way to avoid the divergence here. But of course that's problematic because the theory is supposed to represent physical interactions. So the coupling should be non-zero. So yeah, it's a problem. It seems to be something serious. The theory has an incompleteness here, or it's effective, it's just not going to be valid there. So I'd say this is like an internal motivation for treating the theory as effective. It's got internal problem here. And yet those who are working on AQFT would challenge that. They would say, no, it's not. If we have the right formulation of QFT, real QFT, then we're not going to have this problem. So they can challenge this. Also, yeah, as I said, this is usually ignored because it's so high. It's way beyond, the electroweak scale anyway. And also, it's way beyond the Planck scale. So we have external motivations for treating QED as effective here. So coming from other theories and other motivations to look for new physics here and not expect this to be a fundamental theory. So we have internal motivation that could possibly be challenged if you like AQFT, but we also have external motivations here. Okay, so I would say this is really kind of challenging, like probably you're here like, yeah, we all know this, we all agree with this, but there's still like in physics this idea that maybe these things are problematic. Maybe they do point to a new physics. Maybe it is an indication of some need for discrete space-time. So Kiefer here, I think he's just expressing the general motivations. It's not necessarily his own personal view. But he's saying it's long been speculated that quantum gravity may lead to a theory devoid of the viscous divergences arising in QFT. This may happen, for example, through the emergence of a natural cutoff at small distance scales, and then pointing to many modern approaches to QG that do have a discrete structure at small scales. So these divergences in QFT are genuinely thought to motivate some sort of quantum gravity theory, but also quantum gravity theory with the feature of fixing these divergences. But I'd argue that although we may have other indications for discrete space-time, other indications pointing us to the need for quantum gravity, these UV divergences in particular in QFT, they're not themselves motivations for quantum gravity, and they're not motivations for a real physical cutoff in the world. But that can be a bit more debatable in regards to the Landau pole. Okay. So then coming to the perturbative non-renormalizability of GR. Of course, like an early attempt at quantum gravity theory, just treating gravity in the framework of perturbative analysis. And it's shown to be non-renormalizable. You get these divergences expected to lead to infinities. And in particular, it fails at the Planck scale. So this approach towards quantum gravity kind of breaks down at the Planck scale and it's not kind of giving us what we want. So for many physicists, this is really promoted as the problem of quantum gravity. And it also further motivates people to search for a UV complete theory. So it's not just that we need another theory to cover the Planck scale. We need one that's going to cover everything in the UV. And this is, for instance, done by analogy with Fermi 4 theory, which was non-renormalizable, but then was revealed to be the effective limit of a renormalizable theory, being the electroweak theory. So the idea here is that GR is non-renormalizable, so it's pointing to the existence of some renormalizable UV complete theory beyond. And string theory really prompts this. In textbooks you'll see, they're just saying, look, we have string theory, it's UV complete, we've got GR as the low energy limit. So this is presented as a criterion of justification for the theory. So Niels and I went quite deeply into this. We wrote a whole paper about it, looking at kind of the general motivations, as well as also looking at it, how it's used within particular approaches, this principle of UV completeness. So basically what we argue is that on its own, this perturbative non-renormalizability of GR doesn't motivate a need for a non-singular theory of quantum gravity, doesn't motivate a minimal length for reasons similar to the UV divergences in QFT, nor does it motivate a UV complete theory of quantum gravity more generally. This, again, the divergences might just be a problem with the perturbative analysis here. And I think I've taken that quote Procrustean bed of perturbation theory from Euclid. I liked it. The idea is that in the full theory, the non-perturbative theory, then it would be renormalizable. And one suggestion of this is in the asymptotic safety scenario. So, basically we argue that the problem here is not the UV completeness, but the fact that it happens to break down at the Planck scale, and it's failing to give us predictions in the domains where we expect quantum gravity to apply. So if you recall the last lecture, the problem is that it's failing to satisfy this primary motivation for quantum gravity. So just as an aside here, Hossenfelder, I wanted to include the slide, but I've lost the internet before. She discusses, she's got a review about minimal length, and discusses this case, and presents, so Heisenberg in the 30s and 40s, he saw the problems with the then fundamental theory of interactions, in particular Fermi 4 theory, and he thought, well, maybe this is indication that we have a minimal length. It was on the order of about 100 femtometers. But of course, that was never found. Instead, Fermi 4 theory was found to be non-renormalizable, an effective theory, and then we went on and of course found electroweak theory, and we didn't find that minimal length that he postulated. So she suggests that maybe by thinking that the non-renormalizability of GR suggests a minimal length in the same way, we'll be making the same mistake as Heisenberg, where instead we might want to look for a new theory that would allow us to probe even greater scales. But nevertheless, so she recognizes that this doesn't count as an internal motivation for discrete structure or minimal length, but nevertheless, we have many other external motivations, so other reasons or other indications that they're a minimal length. And so this is kind of consilient with those other external motivations. So I'll just show this because we presented this paper at a conference in Munich in 2016. I don't know how to use this. Okay, big. And then make it big. Okay, I don't know how to make it bigger. Sorry, you can't read it. Chris, how do you increase the font size? I can't work Macs. But anyway, we presented it at a workshop in Munich, and Hossenfelder was there. I'm sorry, it's like way too small to read. But basically, yeah, she's reflecting on being invited to speak amongst philosophers. She goes through, gives a nice review of all the talks at the conference. She says, you know, Butterfield is very insightful and reasonable. Going down, she really likes Radin. You know, he's not disappointing. I also believe that Radin has a bright future ahead. And then the final session on the Tuesday afternoon, the most physics one. My own talk about the arguments of naturalness was followed by a rather puzzling contribution by two young philosophers. So we don't get named. They claim that quantum gravity doesn't have to be UV complete, which would mean it's not a consistent theory up to arbitrary high energies. It's right, of course, that quantum gravity doesn't have to be UV complete, but it's kind of like saying that a plane doesn't have to fly. If you don't mind driving, then why put wings on it? So if you don't mind UV incompleteness, then why quantize gravity? So yeah, we were pretty proud of this because, like she says, this talk confused me because the argument wasn't wrong, but for the practicing researcher, it's just remarkably irrelevant. So yeah, our moment in the sun. But yeah, interesting here as well. She says, our first concern is to find a promising problem to work on, and that the combination of quantum field theory and general relativity isn't UV complete is the most promising problem I know of. So she is recognizing that this is interesting and it's motivating something. It's motivating further research. The perturbative non-renormalizability. Okay, so how do I get back to the slides? Can't work Mac. Thank you. All right. So, from that discussion of the QFT singularities, we can recognize four different, well, hang on, this isn't the four different attitudes. We can recognize several different attitudes here. The first one is that the singularities in QFT motivate a new framework of quantum field theory as quantum field theory. So AQFT, so quantum field theory without the divergences to begin with. Or you might say that these singularities do motivate a new, more fundamental theory of high energy. And they motivate treating our theories as effective, being consistent with those other external motivations for treating the theories as effective and looking for quantum gravity. So we call that the new physics view. The numbers in the brackets will correspond to the four attitudes towards singularities in quantum gravity. So these ones map onto different ones of those. We also have the effective theory view. Here you kind of just ignore the divergences in GR, QFT, since we have external reasons for thinking of these as non-fundamental anyway. So the difference between this and the second one is that here you're only looking at the external motivations, and the singularities in the current theories, you're not bothered by them because you have those external motivations. Whereas the second one, you are saying that they are also motivations. Okay. And then you might have this asymptotic safety view, where the singularities don't motivate new physics, because they're just artifacts of perturbation theory. In the full theory, they're not going to appear anyway, so don't worry about them in this case. And finally, you might have this emergent physics view. So treating the singularities in QFT as being physically significant, but not motivating new physics. You might want to just keep them in there because they're important for other reasons. So I have in mind here Badderman's idea of singularities, where they help us understand emergent physics. Okay, so those are the different attitudes towards the QFT singularities. We'll now look at kind of the different attitudes you can have towards singularities more generally. So, do singularities point to the need for quantum gravity? This is the main question. And we found, basically we did a survey of the literature and said, kind of just looking at what different people think, and that's how we found these 4 different attitudes. So it's just based on a survey. It's not like exploring all the philosophical possibility space or anything. No, we went out and looked. So the singularities are resolved classically, the singularities point to quantum gravity, peace with singularities, and indifference to singularities. So only one of these attitudes, the second one there, says that singularities motivate quantum gravity. So as I said, you can take different attitudes towards different singularities. Yeah, so I'll just present each one of these with some examples, but just to warn you, I'm not like an expert on all the examples because there's like a lot of different literature surveyed here. But maybe some of your favorite approaches are part of that, and that's cool. So the first one, attitude 1, singularities get resolved classically. They don't point to quantum gravity. So again, this is like the AQFT view, where the singularities are to be resolved kind of at the level of current theories. So you don't need to look at QG to resolve it. So yeah, there are different ways of doing this, axiomatic QFT or actual classical ways of getting rid of the singularities in GR. So one way of this, kind of smearing out point particle here, higher dimensional resolution of certain black hole singularities. So some 4D black hole solutions are non-singular in higher dimensions and might avoid the singularity theorems. We also found these things called Crowther stars, which I thought was kind of cool. So proposed by Mazur and Mottola in 2005. Yeah, I just put a couple of slides on this because I thought they're kind of cool. We have this, they're promoted as an alternative to black holes. So Crowther star being a gravitational vacuum star. The idea is that you have this thin shell of matter, and on the outside you just have regular Schwarzschild metric, but on the inside you have de Sitter metric, and this inner region has some dark energy-like behavior that prevents the formation of the singularity. So you've gotten rid of the singularity. You also don't have an event horizon. Yeah, it's kind of like a gravitational Bose-Einstein condensate. They say it's got no energy in the ground state. But on the outside, it looks very similar to a black hole, is the idea. Can consume matter and so that's one way of getting rid of the singularities. Yeah, and they also argue that maybe this can be an explanation for the origin of our universe. Somehow, when they get created, they have the matter going through the central hole and exploding out. So I thought that was pretty fun. Okay, so the next attitude is the one that says we need quantum gravity. The singularities are pointing to the new theory. So they're not going to be resolved in our current theories. The new theory is going to somehow resolve them. So here you can think of it, most physicists kind of take the singularities as many, they like it as a concrete problem to work on, as Cosmology said. So you can take singularity as a guiding principle. It might also serve as a criterion of theory selection, so meaning that any prospective theory of quantum gravity shouldn't be accepted unless it does resolve these singularities. Also, you might think that even if the singularities themselves don't motivate or not necessary for a quantum gravity theory to resolve them, nevertheless, your proposal that you're working on, your approach, does naturally feature a way of getting rid of the singularities. You might promote your approach because of this fact. So a means of showing that it's pursuit-worthy or non-empirical confirmation. So, yeah, again, this is this intuition that, you know, the singularity is kind of a locus where new physics can be expected. But it needn't mean that the singularity itself is a physical event. So Ravelli and Vidotto say the Big Bang singularity does not appear to be a physical event, but only an artifact of the classical approximation. In this, it's analogous to the possibility of an electron to fall into the nucleus of an atom, which is predicted by the classical approximation, but not the quantum theory of electrons. So this analogy between kind of the Bohr picture of the atom, which had some singular behavior, but it got resolved, of course, in the quantum theory. So the idea is that, in a similar way, the singularities here point to the need for the quantization of space-time. So I just skipped that. So some more examples of this attitude, so how we might resolve singularities in different approaches to quantum gravity. So Bogerwald has this one, where we have there's no longer the Big Bang singularity. You can proceed in discrete steps through this model and pass through the Big Bang singularity to pre-Big Bang era. So that's one approach. Another one from Ashtekar and collaborators, where we have this dynamical resolution of the Big Bang singularity. Instead we have these bounce models. So here again, the quantum evolution is non-singular across the quantum regime as we go through the bounce. Yeah, and another way in which singularities could be physical here, might think that there is some physical place or time, even if classical GR doesn't describe it. So maybe the classical singularity doesn't represent the final frontier, and that we have a physical space-time, but around the Planck regime, fluctuations become so strong that we also have space. So for this idea, it's like classical GR can't be extended in here, but we need the quantum motivation. But that one, again, could motivate either quantum gravity or a resolution at the GR level. All right, attitude 3. Here we just have peace with singularities. So we just don't resolve them at any level. Don't resolve them in your current theories. Don't resolve them in quantum gravity. Don't resolve it even in a fundamental theory. So reasons why you like singularities. Not treating them as indications of limitations of our theory. So different ways of, or examples of this attitude. You might think that the singularities are predictions, so we don't need to get rid of them, we shouldn't get rid of them. They might be somehow explanatory within your theory without needing new physics, or they might be required for stability. So for the first attitude, I have in mind this Meissner and Ullmann tolerance for singularities, where they're treating as predictions of GR. And for 3b, this explanatory idea, again, Batman and Roman Dachau, emergent physics view, where the singularities are necessary for an adequate description of the emergent physics. And this third one, where they're required for stability, we found this from Horowitz and Myers. They argue that a modification of GR that is completely non-singular could not have a stable ground state. The reason is that such regular modifications of GR would have to be completely regular solutions with negative Schwarzschild mass. So if you want the theory to have any stable lowest NA solution, it must have singularities. So here you'd want to keep it in your theory of GR. And finally, you might just not care about singularities. They're in GR and QFT, which we're expecting for external reasons to be effective theories. So looking at other motivations for quantum gravity aside from singularity. So the singularities don't need a resolution, but they're also not telling us anything interesting. So I would maybe suggest that David has this view in regards to the UV divergences. We have external reasons for thinking that this isn't the right framework at high energies anyway. External reasons for looking for quantum gravity. So we're not going to learn anything from trying to deal with these singularities. And yeah, of course, say external reasons, but within the framework of quantum field theory, if you're just thinking of it as neglecting GR anyway, that itself is a reason for treating it as a non-fundamental framework. And also, Seb found this quote from Hossenfelder, where she says the Einstein-Hilbert action is not the fundamental action that we can apply to high energy scales. So we just don't worry about its perturbative non-renormalizability, which is in a bit of conflict with what she said before, where it's a really interesting problem. So a bit of a disagreement there. Should just ask her, I guess. Another example, of course, Curiel, this argument that the singularities, the geodesic incompleteness, not a problem for GR because these just aren't points in theory. And this one from Brandenburger and Vafa, quite interesting as well, where they use kind of T-duality to argue that even though we have a cosmological singularity in the metric, the string just kind of doesn't see it. So we can ignore the singularity because it's not really a problem for the string. Okay, so that's it. Those are the four attitudes that they're resolved classically or level of current theories. They might be resolved in quantum gravity. You might just have peace with the singularities because you like them, or you might just not care about them. So we conclude that singularities by themselves don't automatically point to new physics. Some of them maybe do. You might think that the resolution of curvature singularities could be expected to give new physics, and maybe the nature of this new physics is going to depend on how you're resolving the singularities. And it also suggests too that your attitude towards the different singularities will depend on your attitude towards these different motivations for GR anyway, the external motivation. So yeah, thank you.
Questions?
So thank you, Karen. I'm wondering to what extent you would say that the four different attitudes exclude one another. So in particular, I was sort of intrigued by your proposal that now Hossenfelder seems to adopt another attitude, and that made me think, well, maybe Hossenfelder would not regard C2 and forwards in conflict with one another.
Yeah.
That from just looking at the low energy regime, we could be indifferent to the singularities, but precisely because we expect them to be resolved in our theory of quantum gravity. So when she objects to the proposal that you and Niels gave, I'm thinking of her saying, well, we have this theory space comprising of theories of quantum gravity. Some of them will be UV complete, and some of them will be sort of intermediate, but we expect that the final theory should be UV complete in the end. And then what Hossenfelder says is that given that I don't know what to put, I don't have a non-UV complete theory of quantum gravity, or at least something intermediate between the low energy version and David described the other day, and then the full theory of quantum gravity, and then the full theory of quantum gravity, you would say, why not just include this principle as well, regarding as a sort of an additional searchlight that is helping me towards the theory, but it probably depends on whether you regard principles as something that blinds you or something that aids your search by making the search space a little smaller, and therefore hopefully sort of giving you a better grasp of what you're looking for.
I mean, we gave a lot of arguments for why you shouldn't even use it why it shouldn't be used as a constraint. We were a bit weaker on why you should exclude it as a guiding principle. But yeah, I won't go into those ones. But into this question, I think you'd just be describing attitude 2, right? If it is motivating you in any sense, then you're in attitude 2 already.
Right, so you still see a conflict in the two attitudes?
Yeah, I think so. I mean, either you care about them or you don't.
Can you explain the distinction between UV completeness as a motivation versus our current effective theories just don't work in the regimes where we want quantum gravity to apply, and you said that was the primary motivation, and I didn't quite understand why they were different.
Right. So,
especially if those regimes are at the kind of
okay, okay, maybe that's the problem, like if the idea of scale is difficult there. Well, it depends on how you set up your motivations for QG. Like, if you want it to be a complete fundamental theory of everything, a unified theory, then yes, it makes sense to include it as a principle, because then you do kind of expect that a fundamental theory covers everything. But if we're just taking quantum gravity as quantum gravity, and kind of just want it to describe these domains where we expect quantum and gravity to be necessary, such as the black holes or the Planck scale, or early universe cosmology, then you might not need it to describe arbitrarily high energies. It might be enough to have an effective theory, as long as it's doing what we want it to do. So yeah, it would depend on kind of what you mean by quantum gravity. So I would argue that it makes sense in an approach like string theory, or maybe less sense in kind of more minimal, modest approaches.
So you're saying so conceptually there's a difference, but it's contingent whether those two principles happen to coincide.
Exactly.
And they do because of the Planck fields.
Exactly, yeah.
David.
I wonder if we should be thinking on this issue about whether the non-renormalizability of GR is a reason to expect to think it breaks down at those high energies. I mean, my worry is sure it could be the perturbation theory is giving us the wrong answer. I mean, there's always a risk when you use perturbation theory anywhere.
Yeah.
But it's one thing to say yes, there is a possible route to quantum gravity that works its way around and bypasses concerns about perturbation. But it's another thing to say, well, because of the possibility of that, I just have no reason to think the theory breaks down. I mean, what's wrong with saying, okay, because of the really strong paternity evidence, the theory breaks down at the Planck scale. That's really good reason to think the theory breaks down. But of course, it's not conclusive reason to think it breaks down. And sure, you can explore an alternative research proposal that lists as well.
Oh, so it can be a weak reason, even though it's not really necessarily motivated.
Well, no, I'm a bit sorry, I'm going to say it's a really strong reason. Just not a conclusive reason.
Right. But, would you say that in the case of the QFT singularities as well, then? Like, in the standard model?
Well, so in the standard model, I mean, yes, it's the short answer. I think the perturbative rate, it's like the Landau pole. The Landau pole, I think, gives you excellent reason only in the case of asymptotically free theories where I think at that point there's a really quite live possibility of mathematically rigorous free combinations that just against it. But you know, I feel a lot more confident about the determinative arguments for break out of non-renormalizable theories at a scale than I do at the Landau part.
Yeah. Yeah, I mean, I can appreciate that, but like, it would be really, I think, a bit. I mean, couldn't we explore more conservative options to begin? Like something like asymptotic safety. Like, okay, yeah, maybe, I mean, I'm not disagreeing with you, I think, like, you could use it as a reason. Just not conclusively. I don't know, I think it might blind you to the other possibilities, I would say. The fact that we do have other possibilities.
But I mean, it's not obviously just that. I mean, Weinberg makes the point that asymptotic safety is a possibility very early on. Everyone is that, they just think it's really unlikely to work. And I mean, it's worth remembering almost everything we know about quantum field theory comes from one or other deterministic approximation scheme. Almost everything we know about almost every theory in physics comes from one or other deterministic approximation scheme. Obviously, they could all break down, but I think if we start saying, well, when we only know about something through a deterministic approximation scheme, we have only the weakest reason to think it's true. That just seems too demanding a standard to place on how we get information from theories.
I don't know, maybe I'm a bit cautioned by that Heisenberg story where he was thinking, there must be. I mean, that still motivated new physics, though it didn't motivate the universe. So maybe that's, so maybe it can motivate new physics without necessarily needing the UV completeness in a particular way. Yeah. Yeah, I mean, I don't have much to say about that, but yeah. Again, I think it would really depend on your external motivations. Like if you have other reasons for looking for new physics here, then this one's considered for that. And if you kind of treat them together, then it becomes more strong.
Does it even have that? I mean, suppose I have a modern vector field theory understanding. My state of the art is the thought there.
Yeah.
And that's all I know. I don't have external reasons to break that. Doesn't the perturbative failure of the Fermi theory at the electroweak scale give me really good, but not conclusive evidence for new physics?
Right.
So conversely, if all I have is GR, I haven't noticed the classical singularity theory. I just noticed that the perturbative non-renormalizable at the back scale doesn't give me compellingly good, but not conclusive reasons to expect new physics at the back scale.
Yeah, I take it. So instead of, maybe I just pushed it too strong. Like saying, maybe a reason, but you can't rule out the other possibility. Something like that.
Yeah, and sure, you can't rule out asymptotic safety.
Is that a follow-up?
No.
Okay. You want-
I have just a very simple-minded question. If
Oh.
someone
Sorry.
Oh.
Johannes first, and then we'll go to you.
Okay, I have a general question about the topology of principles. Today, you suggested in your talk that the principles that you discussed today can play all the roles except for being a postulate. At least you didn't mention that they could play that role, which made me thinking that maybe there is an important division between principles into those that can play the role of postulates, so that they are assumed at the beginning of our theorizing and are like building blocks of our framework, and there are other principles which are not candidates for postulates, but rather they concern the outcomes of developing our framework. Would you agree with that?
Yeah. I mean, I think we're trying. Oh, I didn't put up on this one. Yeah. So being a postulate, I think of it would also serve as a constraint. If you put it as a postulate, or a criterion. So maybe I kind of lumped those two together. But you're right, it's a different idea. And I think I would agree with you, maybe we have different types of principles. Yeah, but you're right, I think this could work as a postulate too, right? Lay it down that the theory is going to be singularity free, for instance. That how you build on that. Yeah, what do you think?
It seems to me that this is something that turns out at the end to be true of both. Like, I build the theory and then I check whether it resolves singularities or not.
Oh, yeah? Oh, but, so then you wouldn't even take it as a motivation? Like,
Yeah, but then, as I see this, this would not be a postulate because it's not like an axiom upon which
yeah,
I do
to build it.
This is something to check at the end whether I achieve this or not.
Yeah. I guess it depends on like how you go to. But where would you want to put your attitude there? Like,
Okay, so you're suggesting that this depends on the theory. Okay. Yeah, so I was thinking about the same.
yeah, because if you're using it at all as a motivation or to check, then it's very.
Sorry. So I was just wondering how someone who defends we should be in peace with singularities would describe geodesic incompleteness. For example, if I'm just standing and free falling with my clock and in a finite proper time, I cease to exist. Is that what someone would say?
Yeah, I think so. I mean, there's problems with exactly how they define it. I think there are other people here who could probably give some more insight into that. But yeah, that's the idea. It's just incomplete, possible world. If anyone else has comments on that, though. Yeah.
Thank you. I would also like to push back a bit about the categorization of these attitudes. I remain to be convinced that particularly the categories 3 and 4 really should be two separate categories. And what brought me to that is the surprising categorization of Erland in Camp 3 and Curiel in Camp 4, because I took them to have the same attitude towards singularities in GR. And now that I'm thinking about it, I'm not sure anybody really is in Camp 4, because you cannot just be indifferent to singularities. Singularities are an apparent problem. Either you resolve them in the theory, sort of internally, and then you're in Camp 1. You resolve them by sort of convincing yourself of the limits of the theory in which they occur, in which case you're in a version of Camp 2, I suppose, and you assume that they'll then be resolved in a more fundamental theory, or you've convinced yourself that there's no problem with the singularities, and therefore the singularities don't require a resolution. But then I think you're in Camp 3, you're at peace with the singularities.
The Camp 3 was meant to be more of a positive attitude. Like you like the singularities and you have positive reasons.
Oh, so you've not just convinced yourself that they're no problem, but you've convinced yourself that you want them.
Yeah, you want them, yeah.
Oh, okay. I see.
But in regards to Kirill and Erman, yeah, maybe I could.
Yeah, then maybe Erman would be more in Camp 4.
I was thinking, he treats it as says we can treat it as a prediction. For me, that seems like a positive thing that you want to keep in, rather than just not caring. Yeah, thanks.
But I think that gets back to my concern whether these are not in the end versions of the two, especially if you think that singularities is sort of a nice features. So suppose Batterman would say it's relevant for emergence, but as soon as you say this is something that is important for certain emergent features, maybe Horowitz would be different, but Batterman at least, then presumably it's emergent from something else, and then at least you are moving towards an implicit appreciation of 2 as well, that you expect the resolution of singularities through 2, but you also appreciate the role the singularities have, for instance, at your higher order level. But maybe it's only a question of how to categorize, for instance, Batterman's attitude in this case. Horowitz might be different.
I mean, I think categorize his attitude right, but someone else presenting the same ideas would take a different attitude. So, by which I mean, he's focused on the emergent physics and understanding that. So he's not really concerned about the higher energy. He's focusing on the low energy, where that's important. So, but you're right, if he was looking at it the other way, you could take a different attitude. Yeah.
Yes, hello. Thanks, Karen. I had a similar doubt that I'm faced before, but now I am confused about how one could be in peace with similarity. I mean, in the sense that you want them, but you don't have a very careful description of them. So it seems to be a very conservative attitude to take. In the sense that you are not pushing your description forward, but just taking conservative, say, okay, the description is fine, we can live with that, but we are not trying to look for something more careful. So it seems like, if you see from a historical point of view, it seems to be like, okay, we are happy with that, let's do something different.
So you think it's a bit of a dead end view?
Yeah, it's like you are not pushing heuristically it seems to be not a very wise attitude to push physics forward. Right?
Yeah, sure, I can see that. Because you're not trying to learn more about your
Yeah,
theory,
you have
you're not
something
trying
weird,
to use it to find a
you
new
have something
theory.
weird, you don't have a very good description of that, and say, okay, it's fine, don't worry, let's do something different. But this is not the attitude that physicists usually take, right? It's
Right.
Like, okay, let's look for something deeper.
But I don't know, I think it's okay. I think you can have positive attitude to them without thinking that we need to further develop the theory in order to account for them. We can use them for other reasons rather than trying to find new physics or further develop that. So maybe conceptual understanding emergence, or this weird, that bottom one where you might need them in your theory for stability. But you could say that even in that case you might wonder why push.
Let me be just a little bit more precise, because you can be happy with having the singularities, but also you can claim that you are happy with the actual description that we have of the singularity. And I think that, okay, you can be happy with having the singularities as something in the world, but probably to be happy with the description that we actually have, probably is something that is taking a conservative attitude, right? It's like, okay, probably we can agree that the description is not quite fine, at least. So if you take this attitude, it seems to be that, okay.
I mean,
I don't know.
assuming that there are no actual infinities in nature or something like this.
Yeah, cool. Okay.
Yeah, I was just wondering, do you think maybe the view where that you mentioned where people say, oh, we need to consider smear dark particles and then we don't have an issue with singularities, maybe fits also in this area where you say we don't necessarily have to consider smear dark particles, but the fact that we encounter singularity shows us that maybe for all practical purposes it would make more sense to consider extended objects, and maybe there are inextended objects and they have singularity, so I can live with them, but practically anything we consider has some kind of extension, so it's fine.
Yeah. I think I agree with that. So what was the, so that was the attitude one.
Yeah, so I was just wondering if maybe the attitude one also fits in the piece with the specific example that you gave fits with the piece with singularities as well, where you say we don't have to get rid of them entirely, but the cases where we have them aren't really relevant.
Yeah, so that's like also the string theory one, where kind of the singularity is there, but you're not concerned. Yeah, I think that's possible. Like maybe we could recategorize that. I think so too. Yeah, it could fit there. I guess it depends again if you're taking it like as a description or not, right? Like you're smearing it out and finding a new theory there. Is that replacing the singular theory or not? Yeah. So different attitudes. Yeah.
Mike.
I guess this is a question about researcher agency at its heart, but what is what would, so you argued the negation of the claim is that singularities would like automatically point to infinity. What would ever be the positive version of that claim? Like in what sense would properties of theories automatically sort of unravel themselves?
Yeah, I mean, that's kind of what motivated me to look at it. It's like the claim made by a lot of physicists. You saw Hasenfelder saying this too, that the singularities imply self-inconsistency. Seeds of their own destruction. There just seems to be the kind of horror of singularities, or this, that they're somehow really, really bad, and we've got to get rid of them. And showing that that's not the case. They don't automatically lead to inconsistencies. They don't automatically lead to problems. But yeah, you still find a lot of these claims that people kind of have this kind of generalized horror singularity. What was I about to say? The one kind of really strongest reason I can think for holding that attitude is the belief that there just are no singularities in nature. Infinity cannot exist in nature. And one reason for this, Hossenfeld has a nice recent video on this actually. I'm a big fan. She shows argues that infinite quantities, they're not experimentally measurable. We can never measure infinity, and so it doesn't have a place in scientific theory. And I think that's probably the strongest argument for that.
Chris.
So I had one small question and then a slightly bigger one. So the small question is about grav stars. So I haven't looked at that at all, but it wasn't clear to me whether the claim was we could imitate a black hole by having this weird dark energy bubble inside something else, or was the claim that we could avoid all singularities for gravitational collapse by the claim that instead of having a gravitational collapse to a singularity, you get somehow this different equation of state and forms a grav star instead of the.
I'm not entirely sure off the top of my head, so I'm sorry.
Because if it's a singularity avoidance claim, it has to be the second. It would be a much stronger claim to say that somehow all collapses
They go
into
into
grav stars. The second question was just, have you, in surveying attitudes towards singularities, noticed any differentiation among physicists employing different mathematical techniques? So there's been a rise of people doing partial differential equations and trying to study the stability properties of solutions and looking at singularities as a sort of different set of techniques. I mean, they're more just, I guess, in stability and overall properties like this, Minkowski space-time, stability, perturbations, that sort of thing. But they are also interested in, for example, showing what kind of initial data would lead to a closed Crowther surface, rather than just putting it in as a geometric condition. So it's interesting just because the initial methods of causal structure don't actually tell you that much typically. And if you had a PDE type treatment, it would tell you a lot more about the singularities. But I'm curious whether those two sort of communities have different takes on singularities or.
Yeah, I'm not so sure either. But you're right, it's an interesting thing to look at. So I'll check. Yeah, I can't think to David.
So the way the presentation was set up was very much looking sequentially at GR and GRT using aspects of singularity, which is fair enough. I'm wondering if, at least in some of the literature, you want to think about them as a little bit more tied together. So here's one way of thinking that GR singularity matter. If you buy the, I don't know, compelling, very strong claim that the terms of non-renormalizability gives us a reason for the theory to break down into curvatures, the singularity theorem tells what happens in nature. On the way to a curvature singularity, I reach a region of Planck curvature. So at that point, if you buy, well, the strong claim is that then GR breaks down because it's non-renormalized. The weak claim, which I think is very solid, is at that point we cease to know how to calculate in quantum theory. Even if the theory is asymptotically free, it's not determinative non-renormalization, we don't actually relation theory. So, you could imagine a situation in which, yes, there were super short curves, there was a high curvature region where the theory broke down, but we have no reason to think about curvature regime ever occurred in nature. And so then you could maybe try to make more peace with it, and think, well, we never know that, and maybe it's scientifically not over-realistic to worry about existence. But the GR singularity thing tells us it's true. They say there will definitely be regimes in which we're pushed out of the main validity of effectively the GR and into the unknown.
And the suggestion was that combined with the following considerations.
Well, it's only because if you just had classical GR, then you can start saying, well, curvature increases about the limit fine, who cares, and maybe it's not like there's a point to give curvature, something like that.
Yeah.
But if I've already accepted the field theory, then it's not, then before I get to my curvature singularity, when I get to my region of Planck curvature, and then my theory isn't failing at singularity, it's failing at Planck scale. I already knew it failed at Planck scale, but only in a very theoretical sense, if I had some ridiculously big particles built. Singularity theory tells no, there'll definitely be places where trying to do low energy quantum gravity ceases to be possible.
I like the idea. I think yeah, this could definitely be some used as motivation. Yeah. And I'm just a bit, I guess, confused because I thought like with the singularity theorem it's more about the geodesic implications.
Oh, so I'm finessing the including curvature singularities and
Okay. So saying these together. Yeah.
So, and I agree, one wiggle room is the singularity and so will the curvature singularity. But I'm saying if I have a curvature singularity, the singularity theorem and it's pointed in the direction of curvature singularities and curvature singularities from an effective field theory point of view, they don't point to the breakdown of the theory at the singularity. They point to the breakdown of the theory at the Planckian scale that I'm going to reach on the manifold. So they point on the manifold on the basis of that.
Yeah. So yeah, I would think that's good. I would take that as motivation for the new theory in which I think something that you could use as base criterion to help define what we expect in the theory to
If I remember the history correctly, I guess a version of what you suggested was taking place when Schwarzschild discovered the Schwarzschild solution originally, that there was a debate whether this was something that actually existed, and if it didn't exist, then perhaps it was not too much of a worry. So that would be sort of the second option, that maybe if we don't have any reasons to expect the singularities to actually occur in the actual world, then we would have more reason to be at peace. But I can agree with you that we do have reasons to believe that they occur in the actual world, and on the way to those singularities, we know our theories break down.
And we had those results very early from the simple Big Bang. Already the nature of Tolman Board showed that in a simple FOI, you could reject it because it was symmetric and see it's not that. You already see it very early.
And I think it is symmetrically when physicists, at least in high conditions, talk about singularity
world's an external reason, right? So I mean, I feel like at risk of blurring the categories. When we get to the point in our space-time manifold where we accept theory breaking down, we have to be making extra theoretic. We have to be making use of extra theoretic resources. And so I feel like this. I don't know, maybe I misfollowed the track, but we were talking in a different category, but helping ourselves to external reasons, which we're supposed to. I guess could you put the final slide that has.
Oh, yes, sir.
Yeah, so the final line here, but one's attitude towards singularities depends on response towards external motivations for non-gravity. And it's an external motivation that says there isn't, so it's channeling Ehrman here. It's an external motivation that says there is in fact still a fact of the matter at the underlying point in space and time where we hit the plane. Say as we're going back. And so I kind of feel like you can be at peace with singularities precisely by recalling that fact, but your attitude ends up being very similar as far as like, ongoing research is concerned. So there's a weird collapsing of categories going on, I thought, in this sort of last little discussion. Because it didn't sound like we were making peace with them in the last couple
No,
of
that was
comments.
more, that would be a reason to motivate.
Right, but I'm like somehow it's simultaneously motivating quantum gravity, but while being completely at peace with them. That's the issue in my mind, or issue.
My brain's just not good for all the discussion already. So you're saying it's particular to Ehrman's view?
I think it's in keeping with the singularities are predictions, so I guess also.
Yes.
There's somehow, I can be completely at peace with the fading out of space and time.
Yeah.
As we
Have
go
the
backwards.
prediction, yeah.
While also being very interested in what happens at the Planck scale in that fade out process if we're going back.
Yes. Yes.
And that's because I'm helping myself to external motivations that have nothing to do with the singularity itself.
Right.
And so I've
Yeah.
made the peace with the singularity in the classical description, but I'm still doing quantum gravity research.
Yeah. I like it. I think that's okay. Maybe you can have these two different attitudes. And yeah, I'm glad you pointed that because I was thinking that too, like the high curvature on the way to the singularity that we think is where the breakdown happens and motivating it there. How much does that actually depend on the singularity? Like you could have that kind of curvature without the singularity too.
Right, so it's not the singularity I'm working on anymore when I'm doing quantum gravity.